Hello and welcome to my week in astronomy. What I found interesting this week in the world of astronomy and astrophysics. And this time I'd like to talk about the launch of the Solar Orbiter. As of recording this, the launch is supposed to go ahead Monday morning. You see, this follows on quite nicely. Last week I talked about the Daniel K. Inouye Solar Telescope in Hawaii, capturing its first image of the Sun. And I pointed out the importance of getting good data on what is going on around the Sun to predict the effect of space weather, which could cause a lot of problems for humanity in the future. In particular, flares and things like that being quite damaging to our satellites and our communications networks. But of course, we don't just have to rely on learning about the Sun from these telescopes on Earth. We could also send satellites, which is precisely what the European Space Agency here is doing. In particular, this satellite will be measuring the properties of the inner heliosphere and the early beginnings of the solar wind. So, for a simplification, the heliosphere is a bit of a bubble, if you like. You have the interstellar medium, all the matter and radiation between the star systems, but our Sun is constantly forcing out a stream of plasma, referred to as the solar wind. And if you think of wind, it's going to be pushing away and pushes out the interstellar medium, as it were. And we have this sort of cavity, if you like, which the Sun is travelling in. And the solar orbiter then, by studying this inner heliosphere, this inner part of the cavity, is primarily focusing on the question of how the Sun determines the environment in the inner solar system. And of course, that environment in the inner solar system is a good thing to get as an ideal of what might affect Earth, or how things happening very near the surface of the Sun might give us an indication of what's going to hit us later. A key point of this is the plan to move the orbiter into quite an eccentric orbit, meaning one tilted in comparison to the plane that most planets roughly align on. It's going to be tilted away from that by about 25 degrees. The reason for this is that the orbiter is aiming to make observations of the polar regions of the Sun. And as you can imagine, Earth observations are quite good when you're viewing near the solar equator, but to get an idea of what's going on near the poles, that's very difficult. So that's what it's doing. What I'll do for the rest of this video is try and talk a bit about what tools it has and go through what it's using to tell us about the Sun. I'll link to ESA's page for the Solar Explorer, which has an enormous amount more detail on this. But in brief, they're generally split into two categories. In situ, which measures the data right at the site of the satellite, and also remote observations, so cameras, images, things like that look further away. I'll start with the images. We've got what's called the Polarimetric and Helioseismic Imager, acronymed PHI. It's used to measure the polarisation of light. And in astronomy, this is really useful. Polarisation of light tells us a bit about the magnetic fields we're looking at. It's incredibly complex, but we suspect that we can tell a lot about the Sun if we know what the magnetic fields are doing. So that's a good thing to look for. The other thing is an instrument called SPICE. It stands for Spectral Imaging of the Coronal Environment. So they're having a lot of fun with these acronyms, I see. And it's an imager for the extreme ultraviolet. So that's the frequencies we're looking at. And an imager, well, it makes images sampling at many bands of frequency. The idea of this instrument is that we can observe emission lines in the extreme ultraviolet. So, line emission, we've got very particular quantum mechanical processes which result in emission at a very particular frequency, with a little bit of variation from quantum mechanics, but there you go. And that gives you something which, if you plot intensity against frequency, would look like a line. If we can find these emission lines, which we know come from particular processes, then we can look for the trace elements in the solar plasma, the things that aren't like hydrogen and the stuff that the Sun is usually made out of, these trace elements. We can infer from that some of the properties of the plasma, from, say, how large this signal is. You also have an extreme UV imager. does pretty much what it says on the tin, takes images in extreme UV. The plan is that looking in extreme UV will tell us a lot about the structure of the solar corona. And as an interesting aside, some frequencies of light are far better to observe from space, and some are good at penetrating the Earth's atmosphere, which is why space missions tend to have a very heavy focus on things like UV, X-ray, gamma ray, and radio is usually done from Earth. This part of UV is pretty much impossible to see from Earth, or at least in any sensible level of detail for doing astronomy, so it's good to have a spacecraft for it. You also have an instrument called METIS, which is a multi-element telescope for imaging and spectroscopy. Again, more long-winded acronyms, but basically you take UV, you take extreme UV, and you take polarised visible light imaging of the solar corona at the same time. Very complex piece of kit, but the short is if you combine different frequency band data sets into one piece of kit, you can get a better understanding than just looking at each one individually, so you do this combining. You've got STIX, which is an X-ray imager, and you also have a heliospheric imager. Basically, a heliospheric imager is a camera, and we can use it to detect coronal mass ejections, which could be quite important for working out what's going on in the sun. This lump of mass flies off the side of the sun, we would want to know about it, you'd want to image it. And that's it for images. The solar orbiter, again, as I said, it combines these with in situ measuring devices, which measure at the orbiter. You've got an analyzer for the components of solar wind, which will measure the distributions in velocity of protons, alpha particles, electrons, and a few minor elements. If we know how fast they're travelling or what that distribution is, we might be able to find a bit more about what causes the solar wind and how it develops. You also have an analyzer for radio and plasma waves. It's essentially measuring the electric and magnetic field around the orbiter over a broad range of frequencies. And we're combining that with a magnetometer as well, which is again another thing for measuring magnetic fields. Finally, you've got a detector for energetic particles on there. Really high energy particles coming out of the sun could be important to understanding it. And we expect, for example, that a solar flare would give off a lot of high energy particles, so tracking where they're from and understanding their timing should give us a far better understanding of these events. So if you put all of those bits of equipment together, you get quite a broad understanding of what's going on the sun. So that's what we've got. Those are the instruments that we've sent around the sun to see what we can find out about it. Hope you enjoyed listening to what I had to say. As I said, I'll link to a far more detailed account in the description, and I'll also link to the mission summary, which is a good quick guide to what it's about. So until next time, goodbye.